In this video, we will be talking about equilibrium. Now, when we talk about equilibrium, especially in statics, what does it mean? Well, the root word for equilibrium is equal. So whenever there's something equal, that simply means either side, the left or the right, is balanced. Just think of it as when you're riding a seesaw with your friend. So to maintain the equilibrium on that seesaw, or in other words, to maintain the seesaw on its horizontal position, just like that, the weight of your friend and you must be equal. So that's equilibrium. Or if you can be equal, the weight of yours and your friend, you can change it by putting an extension. Suppose your friend is lighter than you. He or she can extend his distance from the fulcrum so that both of you can maintain the seesaw balance. So that is equilibrium. So in statics, there's two types of equilibrium. One is the equilibrium of a particle. It simply means that the forces that acts on that point or particle are all balanced or equal. And whenever there is a balance force on a particle, the sum of the forces on that particle, let's say in the x and in the y, would be 0. There's no motion. That's why it's 0. From Newton's law, F equals ma, and a there is acceleration, and since Newton described acceleration as the change in velocity with respect to time, and in here, there is no change in velocity either. Yes, there is a mass, but since a is 0, therefore, the overall force, the net force that acts on that object, the net, meaning the resultant, is 0. There is no net force acting on that. That's the first type. And the second type is the equilibrium on a rigid body. What do you mean by a rigid body? There's the first type, and then the second one, equilibrium on a rigid body. A rigid body in statics is similar to a magical thing because this object never deforms, nor bent, or stretches, or even sinks the size. It is assumed that in statics, this object never deforms. It never elongates. So that's what rigid body is. And unlike on a particle, there is three equations involved in the equilibrium of this one, rigid bodies. So here we have sum of the forces in the x equals 0, since equilibrium, as we say. Sum of the forces in the y equals 0. And the third one, that's if new to this channel, or if new to statics, that would be the sum of the moments on any point on that body would be 0. So that's it. The sum of the forces in the x and y for equilibrium of a particle is 0. For the equilibrium of forces in the rigid bodies, the only additional here is the sum of the moment is equal to 0. Well, the moment is the force moment is just the force times the distance. But unlike work, we know that work is also Fd. The d of this moment is the perpendicular. So whenever we have a point here, point of interest, and let's say this is the rigid body we're talking about, and this is the force. Our concern here is either we take the component of this force, it's like that, or this one is equal to this one, and this is the perpendicular one. This force component Fy, let's say Fy, and then this distance, that's the moment. Or what we can do here is the moment arm, adjusting the moment arm, and this is the F, let's say, something like that. And we can see more of this to the example I will show you later on. So in here we have the example On the equilibrium of a particle, on the left, this one, and on the right, equilibrium on a rigid body. So, let's try this example to show you what I mean for this equilibrium on a particle and equilibrium on a rigid body. So, in here, we are tasked to find the tension on each cord given with this configuration. There are a bunch of ropes. This one are cords, that, here, and here. And we are tasked to find what would be the pangusog, pilay pangusog ani nga rope, ani tanan each. So to do that, we consider the particles, particle 1 and particle 2, or a point, as we say, nga wherein na concurrent ang kini nga system, because technically these ropes supports these loads or weight 300 and 400 pounds from falling. So that's why it is in equilibrium. It supports these weights from falling. So the better way to solve this is to start on the very least number of unknowns, because as I've said, the equilibrium on a particle has only two equations, sum of the forces in the x and sum of the forces in the y. That's why we can only solve at least two unknowns. And take a look at this number 1. If we solve this one particle on that point 1, we have two unknowns. This one, or I mean three unknowns. This, because this rope is equal to this rope, so that's why it's okay. It's known. We have three. This one, A, B, and C. So that's the unknown. But if we start here at C and D, and this per 100 pounds, we have only two unknowns, so it's okay. We can answer the what's C and D, and after getting C, we can go to in this point 1 and then solve for A and B, since we know these two already after getting from here. Right? So by doing that, drawing the free body diagram of this point C, or point 2, this one, we then have this. Below is 400 pounds. 400 pounds. This is point 2. And we're given with the angles, which is, with respect to this one, as we can see, these two are parallel lines traversed by this one. Therefore, if this is 30, then this should be 30 as well. So this is 30 degrees. And then we're given with 75 degrees. So this is tension D. That's tension D. And this is tension C. So by the equilibrium, if we draw some arbitrary axis here, it's like that, or that, say this is x and y axis. By summing all the forces in the x and y direction, we will get these numbers. TD for x, let's start for x first. What do we have? Sum of the forces in the x is equal to TD sine of 75. TD sine of 75. This one minus this one is equal to 0. That's the only forces acting on the x direction. Minus TC sine of 30. Sine of 30 is equal to 0. So this would be our first equation. And then for the equation on the y, we have this component plus this component minus the 400. So TD cos 75. TD cos 75 plus TC cos 30 minus 400 equals 0. Or we can transpose this constant 400 to the other side, so we can have 400 right here. And then by using our calculator, the system solver, two equations, two unknowns, we can solve for TC equals TD. TC and TD. So let's try it. For equation solver, two equation, two unknowns. Solve system equation, two unknowns. So for RA, let A be TC. So sine 75 and negative sine 30. sine 75. No, this is 75. Then negative sine 30. And then our constant is 0. Then for the TD on the second equation is cos 75 and then cos 30 and then 400. Cos 75, cos 30, am I right? Cos 30 and then 400. 400. So we have this x means that TD, which is 207.06, 207.06 and 400. 207.06 pound and 400 pounds. This is TD and TC. So now that we have TC, we can draw a free body diagram of this point 1 given this, and we just calculated TC. We can now solve for TA and TB. And then, what else? This 30 degrees, 300 pounds, this TB. What would be the TB? In the problem, this one is actually 105. I forgot to write. The angle from this 300, between 300 and this B is 105. And therefore, this angle here, ano siya, from the horizontal to B, is 105 minus 90. So that would be 100 minus 90 is 10 plus 5 is 15. This should be 15 degrees, right? 15 plus 90 is 105 degrees. So right, this should be 105 and this should be 15 degrees here. So now that we have that, we can now solve for TA and TB. The sum of the forces in the x and sum of the forces in the y. Let's do that. Sum of the forces in the x is equal to 0. So what do we have? This one, and then this TA. So TB cos 15, TB cosine 15 plus 207.6 or 06 cosine, oh no, it's sine, this one, sine of 30, that's minus TA equals 0. And then for the sum of the forces in the y equals 0. This is TB, this one, and this one. There are 3. So TB sine 15, TB sine 15 minus the TC, which is 207.06 cosine 06 cosine of 30 minus 300 pounds, or 300 pounds if we transpose. What else do we know? Oh, we can already get TB right here, because there is only one unknown on this equation. Alright, so after getting TB, we substitute that value to this one, or to this one, and now we get the value of TA and TB. So after solving these equations, now we got the tension in A, which is 1892.38 pounds, and tension in B, 1851.95 pounds. So we've answered this problem, the tensions on the ropes. These numbers here will give this system an equilibrium. So moving on to the next type, which is the equilibrium on a rigid body. Here we have an example. We have a simply supported beam. This is a beam, a rigid beam to be specific, and being supported by a hinge. A hinge is something like you can see on the doors of your houses, in your home. Ang katong mutuyok, itulod nimo ang portahan, katong sa pinakakilid niya. And that hinge prevent motion. The hinge prevents the door from falling down. Also, it prevents the hinge from going rightwards or leftwards. And the reaction depends on kung imo ni siyang itulod paingon didto ang kaninga beam, mupugong ba ni siya? Since ang hinge mupugong na siya horizontal and vertical motion, this would be the reaction. Then the reaction is going to the left since this force is going to the right na siya ana nga component. So that makes it equilibrium. And for the roller only support vertical motion and not the horizontal. So it only has reaction By, as we assume, and then Ax for this and AY for this. Now for this 30-pound force, it has two components, which is this one and this one. And this component is 30 cosine of that angle 30, because this is the one adjacent to the angle. And then 30 sine 30. And then we are tasked to find the support reactions. The support reactions here are AX, AY, and BY. So to find the support reactions, we have these equations. So if I choose to start with the summation of moment, I can choose at B or at A. But suppose I am wise enough to choose A so that I can knock down these forces. Any forces that goes through the point wherein you're taking the moment automatically becomes zero because there is no moment arm on that. So if you take moment at A equals 0, these forces, that one, the only force that would balance that is this component. What about this one? Well, that component acts here. We can resolve that force here. So that's a force that passes through the point wherein we're taking the moment, so that would be 0. So with that, the moment is 12 by. This is the force, and this is the distance, perpendicular distance, like that. And then 30 sine 30 is equal to 12. 30 is equal to 12. Or, in other words, if we take the forces in the y direction di, we can get the same. Or could we? AY is equal to AY plus BY. These are the forces that supports this force, the vertical 30 sine 30. In here, we know that BY is equal to 30 sine 30. So this is one of our answer. And then, substitute that here, we can get AY. So that would be the reaction. Then for AX, the only forces that acts horizontally is this force only. So, AX is equal to 30 cos 30. I've just shown you the applications, forces on a particle, equilibrium of forces on a particle, and equilibrium on a rigid body. So thank you so much for watching. Hope you get something here, or maybe you're confused, but just don't be shy to ask me. Feel free to comment down below your queries, and once again, like, share, subscribe to this channel.